with situations where we need to interface with foreign code. Since in various fields, this is something that sort of you have to go through. And it is quite annoying to do that for various reasons. But the main problem is that the Haskell environment is quite rich by now, so there are a lot of libraries. There are a lot of people also developing libraries in the areas we're interested in, like numerical or scientific computing or like data science and these sorts of fields. The thing is that in these fields, probably many others, practitioners really trust certain libraries and certain tools and really rely on them in quite a critical way. And so we're kind of forced to use foreign code in this case. And so, for example, with C, you can use C in Haskell fairly easily. The foreign function interface of Haskell is very sane and very easy to use. But if it kind of gets in the way of rapid development and sort of iterating and sort of developing code nicely. With languages like R, which are used, for example, in data science, it's almost like, it's not impossible, but it's very annoying to use it effectively from Haskell. So in general, prototyping Haskell code and developing Haskell code quickly when you need to interface with this kind of foreign code is quite annoying. And we've developed two similar solutions to make this situation better. One is inline C and one is inline R. Inline R was authored by my colleague Matthew, who I think should be here somewhere. You were too close. So yes, and then we kind of co-authored the inline C a bit later, borrowing ideas both from inline R, which was called H at the time, and also from previous work by Manu Chakravarti, who did a very similar library, but like the intent is very similar, but the interface and the general ergonomics are quite different. So let's just jump right in. What does inline C let you do? This is a Haskell program, but as you can see in the middle of it, there are 3 lines of C code, right? In this case, we want to parse a floating point number from standard input. When doing this with the scanf function as provided by C. And the piece of C code that you see here appears right in the middle of Haskell code, right? Which is why this library is called inline C. And I think scanf is also a decent example, because if you want to build bindings, like general bindings to scanf, if you want to build a nice Haskell interface to scanf, it's not so easy. This is a contrived example, but there are many situations where you want to sort of zoom in to a fragment of an interface and do not have the burden of coming up with a nice Haskell interface around it, right? So this is the sort of thing we're aiming at here. So let's see what's going on here. The C code is spliced. Well, it's written in a quasi-quotation. So quasi-quotations, for people who are not familiar with them, they're basically ways to have custom pieces of syntax which generate C code, which generate Haskell code. So what they're providing, this C block function, will basically take this piece of C code and produce some Haskell expression. So when GHC runs over this file, it's going to use this function to generate from this C code some Haskell expression. This is a very nice facility without which it would have been totally impossible to do this kind of work. And the quasi-quote we're using here is a block. So C.block. I'm not showing the full imports here, but it's a function provided by inline C. It's a quasi-quote provided by inline C, and it's basically used to insert multiple statements of C code inside Haskell code. Now, the C code itself, it's braced in this typed block. So what we're indicating here is that this C code should compute a float, right? Should return a float. And these typed blocks, you should really think them of like anonymous C functions, sort of. They're like C functions, but without arguments and without without arguments and without a name, right? It's just indicating the return type of this C code. And as you can see, we're declaring a floating point number. We're scanning a float into it, and then we're returning it. So it sort of reuses normal C syntax for functions and for returning values. Now, another thing to notice is that we're including C files at the top level, C header files at the top level, sort of like if we were including Haskell modules. So we wanted to make this very natural too. And this is a template Haskell expression. You basically, again, write a piece of, write this include statement. What will eventually happen is that some Haskell code is being ran to make things work out properly. But it's not, it's a top level thing, but it's not a Haskell definition, right? It's just a piece of code that will be executed. Now, we've shown one side of what's useful in inline C, which is getting data out of C. The other thing that we really want to do is also using Haskell data from C code, right? In this example, we're computing the volume of a sphere with C. There are going to be a lot of contrived examples, but that's the nature of these presentations. And what I have here is the radius. This is an argument to the Haskell function. And we want to use it in the C code to compute this volume. The way we bring this Haskell variable into the C code is by using anti-quotations, which is this, this expression enclosed in parentheses and with this leading dollar. So the term anti-quotation is borrowed by template Haskell again, because with template Haskell you can also anti-quote things. But it's in general when you have this piece of foreign syntax and then you want to bring in something from the outside environment. In this case, the thing we want to bring in is a Haskell variable. So what happens here is that we have this formula here. We also use a macro from the header, for example, which is something we often want to do. And then we want to say, we want to bring in the radius from the Haskell environment. And we do that by using this anti-quoting syntax. And then we have a C syntax, a C declaration syntax. It's like you were declaring a variable of type value in C, but you use it to bring the variable in instead of declaring it in C. We reuse the declaration syntax because it sort of does the job. It's a type plus a variable name, and C programmers are probably already familiar with it, even if it can get ugly, as we will see. So all right, so the C declaration has two parts. R is what we're bringing in, and double is the C type that we want. So this is quite interesting. When we're bringing data in from Haskell to C, we're always specifying the target type. We're always telling inline C, we want something of type double. We're not specifying the Haskell type at all. In fact, the Haskell type is sort of both the return type and the type that we need to bring it in. They're always automatically derived. So in the previous example, actually, this X variable would be automatically derived to be of type float. The type is mentioned nowhere here, but it will be of type C float. And we'll see later how that happens. But a general principle here is that we want to be quite explicit on what target type we want. Since this decision is both because it's quite complicated to do it the other way around, and it's also nice, I think, to to bring into C with explicit types, since if we do some mistakes, the C-type system is not very good at sort of catching them. So I think it's quite good practice to say, I want a double here. Right, so you're saying I want something. By the way, interrupt me whenever you want, since I sort of tried to make the interesting part at the beginning, so we can stretch the beginning. Now, I'm saying I want something of type double, and I want it to be taken from R. This is going to be converted to a Haskell type, and then there's going to be, it's going to be passed as an argument to the foreign C code, basically, and there's going to be a type check that that R is of type C double.
But double is a Haskell function, right?
This?
It appears inside
No. The anti-quotation is just a C declaration. Oh. It's not a proper anti-quotation in the template Haskell sense. So this is custom syntax. Like we have our own parser for this and our own, as I will show. So right, this might be confusing. In template Haskell, when you anti-quote, you have Haskell code inside. This is not Haskell code. It's just always a C declaration. So thanks for the question. Yes. Right. Sorry. Another thing to notice is that we're returning IO C double instead of just C double. This is also something that you can make a judgment about, in the sense that we chose to always leave in IO when dealing with foreign code, because that's the most honest thing to do, since C can do whatever it wants, really. Like Simon told us how we don't get segfaults in Haskell. Inline C is a very easy way to get segfaults, but like even just side effects are just very easy to perform in C. So we chose to always work in I/O. And if the user really wants sort of a pure expression from a bit of inline C, it needs to mark it explicitly. We not say perform I/O. There are also technical issues because here you're splicing some foreign code inside the Haskell expression. It's not very easy to make sure that this expression will not be inlined in an inconvenient way, because you can only mark top-level definition as no inline, right? So another thing we wanted to do is to be able to use Haskell data structures in C in a nice way. So we want to be able to sort of get a C representation of our Haskell data structures quite easily in the inline C. So in this example, we have a vector of integers, and we want to get the average. We're defining this function in C with a bit of inline C. If you take a glance of this, it looks very familiar in the sense that you're accumulating the total value. You're summing up all the values in the vector, and then you're dividing by its length. But what's happening is that we have this access argument, which is our vector. And then to use it from C, we really want two things. Its size and a pointer to its contents, right? And we have, so if before we had sort of a simple anti-quotation, which simply mentioned the variable, here we have some more fancy anti-quotation. So this $back length will extract the length from the vector that we're mentioning. This back pointer anti-quoter will get us a pointer to the beginning of the vector. So, so we can get the information that we need to work on this vector easily. And that this is very convenient. When you're often working with this set of structures, being able to quickly use them in C, yeah, it's quite convenient. Note that, so when you're getting the pointer, again, you're mentioning what the target type is, what the target type in C is. So we want a pointer to an int, right? And this isn't constant in this sort of, when we're dealing with C. In inline C, we always are very explicit with the types of the target C data. For backlen, this is not needed because it's always int. It's never a choice. Like it's always the same target type, so you don't need to mention it.
Where's backlen and backpointer? Where are these defined?
I will talk about this. Like it's this is completely user defined. It's not like baked in. Yeah, I will explain how this works. They're not Haskell function per se. There is no identifier called backlen in Haskell, but it's, yeah, there is a way to define this. Finally, another functionality which is useful and kind of comes out of the box, like the functionality with vectors. We have, by the way, we have very similar functionality for byte strings that come with the library. It's basically the same thing, but the pointer type is always char pointer. Yeah, the last thing I want to show you is Haskell function in C. So yeah, that's a typo, but you often want to, especially with certain libraries, you often want to call back into Haskell from C. This is quite cumbersome to do manually. It's very nice that you have the facility to do this at all quite easily, but you have to define these FFI wrappers, and it's not too, yeah, you have to sort of, it's not like immediate. It's not as easy as we want it to be to develop software quickly and nicely. And inline C offers you a facility to do this. So this vector map function basically accepts a function that transforms a double. Again, the return type is in I/O, because here everything lives in I/O when dealing with C. And then applies this function to every element of a mutable vector, kind of destructively updates it, and then finishes executing. Now, this function has two arguments, the function itself, f, and the vector xs. And we want to be able to use f from C. So here we're getting the pointer to the vector in the way we've seen before. We're also assigning it to a variable so that it's not, we don't need to continuously mention it. We're getting the length directly here. And then here we're getting a function pointer to the Haskell function. And we do this with this fun anti-quoter. So we have backlen, we have back pointer, and we have fun. And again, using C function declaration, this is when it's ugly, because C declarations, I don't understand how they came up with this syntax. Like, even like, I mean, I understand that you didn't set this up front, but it's just very counterintuitive. I actually really learned C declaration syntax just by implementing its parser. I don't think there is any other way to sort of truly learn it, and which I had to do, as I will explain later. And in this case, this means I want a pointer to a function from double to double, and I want it to be taken from the Haskell identifier f. And there would be some magic going on, allocating a function pointer and sort of giving it to the C code and so that you can use it easily. And then you invoke it directly on the element, and then you assign the element to the new value. Right. Sure. To the average one?
Oh, the next one.
Yeah.
You have between brackets and the I?
Yes.
Okay.
Yeah, thanks for pointing it out. I must have copy-pasted something. Maybe, you know what? I started with this in line, then I realized, no, I actually need to move it out, and I didn't remove the indexing. Yeah. This is not allocating anything in the loop, so it's not like there is some allocation going on. I mean, it's a good question. Every anti-quoter is sort of completely static in the sense that nothing happens in the C code to make the marshalling happen. It's all upfront. So in this case, I mean, I understand your worry. Like, you don't want to allocate function pointers at every iteration, but you can. The annoying thing is that one annoyance I have with this sort of syntax is that if I wanted to define the function pointer before, like I did here, I need to mention this type twice. I need to say, I want a function pointer from double to double, and then I need to invoke the anti-quoter, I need to mention this type again. And the reason why that is the case is that the anti-quoters are parsed very locally. You have no knowledge about the external C code. It would be nice to have some sort of inference of this kind, but it would be nice, but also sort of complicated. Future work, yes, soon. I'm declaring it and applying it, yes. I think, yeah, if I get time to explain how this works, it would be clear.
So you could just say, after the first double...
I think what the thing is that I could simply say double parents star G double equals, no, but I would have to say the entire thing again. This is the part which I don't like, that we have no knowledge of the C code, and so we can't do inference. I mean, sometimes, in this case, you really need to mention the type, because C can't possibly know what the type is. But in the case where you're assigning it to something, you know what the target type is. It would be nice to infer it, but currently, yeah, we can't. Future work, yes. What else? So this was sort of a roundup of what you can do with what comes out of the box in inline C. So what can we do? We can embed arbitrary C code in Haskell. Main feature, clearly, inline C. You can write some Haskell, then write some C, then write some Haskell again. Very nice. You can capture arbitrary Haskell variables and use them in the C code. Now, I haven't really mentioned what you can capture. Of course, you can't capture everything, or it might not be useful to capture everything. What you can capture is really what's an instance of storable in Haskell for the default anti-quoter. For more complex anti-quoters, like back pointer and back length and so on, they do something to make things happen. You can quickly use these Haskell data structures in C with these custom anti-quoters. You can use Haskell functions as C function pointers, and you can include C headers to use easily to use the definitions that they define in the inline C snippets. So everything, like of the things I've shown, like the core of inline C is everything apart from backline, back pointer, and fun, the additional anti-quoters. So the core of inline C sort of defines a way to splice the C in, and the default anti-quoting mechanism. But then everything else is extensible by the user. So these facilities for vectors and for functions are not baked in, are like defined as additions, basically. And the user can extend inline C in two ways. One way is adding these new anti-quoters to sort of support data structures or do even file scripting. The other thing is to just add more C types that you support. So up to now, we only see standard C types, but you can add more. And each module where you use inline C has a context where you specify which addition you're using. It's sort of like language pragmas in Haskell. You're basically saying, oh, I need to add support for these types, and I need to add support for this anti-quoter, and you sort of specify it at the top level, as we will see now. So in the example before, this will be a full Haskell file. This got a I mean, it probably compiles. I haven't tried. Actually, it doesn't because, well, it does, but it doesn't work, maybe. But like this kind of shows all the elements that you need to make things work. So you have some imports. So we're importing language C inline, which is the module that inline C provides. We're importing qualified. We're importing the vector library. We're importing the module exporting C types. And then here we're saying, I want the base context, which provides support for C99, basically. Then I want the vector context, which provides back pointer and back length. And I want the func context, which adds supports for functions. So these are sort of modular, and you can combine them with the monoid interface. And we found it useful when you're using a big library to define a context for that library. And when you want to use things from that library, you just use that, and it defines all that you need to do common tasks there. So I've shown these anti-quotates. Now I have a little example for additional types. This is quite common in C libraries. Let's say that we have this computer science library that does as if P is equal to MP today. They often define bool to be int and stuff like this. And so you want to be able to use these types in your inline C. And some details are omitted here, but basically you can do this by defining a new context, which lets you write the type itself in the inline C. And it also lets you, like inline C will convert it to the right Haskell type when the C function executes, basically. So in this case, we're taking out something of type bool, which we've mapped to a data type we define, probably containing a C integer. And we're converting to a Haskell Boolean with this function. Yeah, we're also including the header and setting the context. But the idea is that you can add all the C types that you want. So this is a real-world sort of use case. So we have these numerical libraries that are very big, like GSL or NAG. So NAG in particular, which is something we use, has thousands of functions, I think, around 2,000 functions, something like this. GSL is also very big, but 1,800 functions for NAG. Okay. So not only there are a lot of functions, but the single, like even if you want to use just the ODE package, sort of, you need to go through this, at least these two functions to get some numbers out. So it's like heavy, right? You don't want to think, how do I create bindings in Haskell to use this effectively? That's how we sort of got started in working on this. I just want to use these functions and get the numbers out using exactly what I want, right? So in this case, this setup function sets up some piece of state. Right, actually, I should say, this is an ODE solver package. It's not important what it does, but like if you have a function, you have a domain, you specify the domain where you want to solve, and you start from the beginning, you start to go forward, and you ask, I want this point, I want this point, I want this point. And it sort of gives you the solutions at the points that you're asking it for. And this is a setup function that sets up some state. This is the range function, which basically, if you are at point X and you want point Y, it's sort of say, okay, advance until you're at point Y and give me the solution at point Y. And here you see you're passing a function pointer in, which is sort of the slope field you're solving. So there are lots of crap, which is not so important now. But that's the point. You don't want to think too much about the things you don't need immediately. You just want to use it in the way you need to use. And so we sort of, in Haskell, what you might do, I mean, I have an example app that sort of does this, and it's sort of similar to what we did at work, is that we ended up with a very simple interface with just two functions. One to set up the ODE solver, so it takes the domain, the initial and final value of X, and then the initial solution, and also a tolerance for controlling errors. And then it returns the state. The state is parameterized over the dimensions of the problem. So this is also very well typed, as opposed to simply having arrays. And then when you want to advance this system, you provide the state. You provide the Haskell function, which is not even in I/O. We sort of simply convert it to I/O in the definition of ODE range. The X value, which you want the solution, and you just advance the system, and you get back to the solution at the value you specified. Under the hood, there is a lot of things that you could abstract over, but we don't. So, for example, the method that you might use, the maximum number of steps, this error handling is sort of more sophisticated in NAG, but we just want to return a string. All these things is sort of paper over, and we provide the interface that we need at the moment, right? Right, so this is a pretty picture. I thought I should have at least one. So it sort of plots the Lorentz attractor with an interface very similar to what I just described. So there is actually an URL where you can run these things. And the nice thing is that you're using the C interface, which is big and old and ugly, and then you're using this very nice library, the charting library from Haskell, and you're using them together in a quite nice way, which is sort of the dream here, right? You sort of can use the nice thing when you can, and when you need to, you can use the ugly part easily. Right, so this is sort of what you can do. So how does it work? How much time do we have? How does it work? Like, the basic idea is that there are 3 stages. Each snippet of inline C is converted to a C function. We also write it to a file. I'm not going to go, well, maybe if I have time, but building these things is a bit annoying, but not as annoying as I thought it would be. But this function will have to be compiled eventually. So we generate a C function for each inline C snippet. Then we convert the C types that are involved in this function back to Haskell types. This is sort of the second stage. And we generate an FFI binding for this C function. And then we invoke this binding, preparing the arguments the way we need to. So this might go from not doing anything, like if you're just bringing a double in, or getting the pointer out of a vector, or stuff like this, right? So this is to give you an idea. If we have this function, which for some reason we want to compute the cosine of a number in C, we can do that. And I don't think I mentioned it as actually. C block is a series of statements. C expression is just a C expression. You don't have to return anything. It just computes that. But anyway, we're using this to compute the cosine of a number. We're going to generate a function that looks like this. It takes one argument, which is the argument we're capturing in, and it just uses it in the way the C code specifies. I call this inline C x, y, z. And then inline C would automatically add a binding to the C code. Why is it? Oh, maybe it's there. Yeah. And now, if you've never seen a foreign function import, what this is basically saying is I want a function of type C double to IOC double. This function doesn't have Haskell code. This function should really, when you need to execute it, prepare the argument so that following the C language convention, right? And then jump to the symbol I'm specifying here, right? So this is the symbol that corresponds to that function. And this is the functionality of Haskell, right? You couldn't write this, yeah, like it's something built into GHC. And then finally, before we had a C expression, a C piece of C syntax, we replace it with an invocation of this binding. And this is really, yeah, this is basically what happens. Oh. Right, so let's talk about these steps in a bit more detail. So first step, we need to generate a C function for every C snippet. So in these snippets, we care about 2 things, really. We care about the return type of this C block or C expression, and we care about the antiquoters. Everything else doesn't really matter to us. And in fact, we would like to leave it alone, right? So to turn this C snippet into a function, the return type of this function will be the type that's specified. Like here, for example, here will be double. This brace block specifies the return type of the function that we're generating. And the arguments will be derived from the antiquoters that we have. So for each antiquotation, we will have one argument to our C function. It's very simple. We also need to, we generate these arguments, and then in place of the antiquoter expression, we insert the argument name that we just generated, basically. We also need to generate a name for the function. This is actually quite hairy for some reasons, but it's actually based on the contents of the function. So it's sort of deterministic. If you write a piece of C code, it would always have the same generated name. It's sort of the hash of the C function, basically. The reason why this is the case is because you often build Haskell objects multiple times, and you always want the same output. So yeah, it's deterministic, which makes things much easier. right, and the rest, after you've done this processing, the rest can be fed to the C compiler as is. You don't need to understand the C code, which is a very useful thing. To give a bit more complex example, if we have this print vector info function, which prints the length and the pointer address of the contents of the vector using printf, and we're using backlen and backpointer to get the data that we need. We're going to generate a function with two arguments, one with the length of the vector, one with the pointer to the vector, and then we're going to replace the anti-quotations with the arguments that we've generated. And as I said, we really do not want to parse C, mostly for two reasons. Supporting every C that every compiler supports, it's an impossible task. You can probably go very far, but like it's always, if you're thinking of GNU or Apple extensions or even inline assembly, we want to be able to not worry about this sort of issues and be able to let the user write whatever C he wants. And the other difficulty would be to come up with a syntax that supports both C syntax, which is actually, it's not a big syntax, but it's not trivial, and also arbitrary anti-quoters that we might want to insert. So it's sort of an annoying and complicated task. So instead, we just do this preprocessing without looking at the C. And to do that, though, we cannot use a parser generated by a YAC generator or like this sort of parser generators, because they're usually not incremental and not, they often go reverse. They often require a lexing stage and this sort of stuff. Instead, we built an incremental parser for C99 declarations using Edward Metz parsers library. It's basically like parsec, but a bit nicer. So there is no lexing stage. We just scan the body of the C snippet. When we encounter the token that tells us that an anti-quoter is beginning, which is $, we just parse the anti-quoter and let the parser finish, and we know when it's done, and then continue without touching the rest. This also means that the user can define their own anti-quoters in a very liberal way, since we can compose these parsers easily, which is also a feature of these parser combinators. And a nice side effect is that I was forced to define an interface for C types, and so we ended up with an interface for C types, which is sort of nice, which is not so obvious. Like it's sort of close to what you would write in Haskell, but many libraries that offer parsers from C give you C types in the sort of the raw form, kind of close to the grammar of C, rather than close to what they mean, and it's just messy. Like the C declarations can get really horrible. The second step is getting a Haskell type from a C type. We do this for the return type, but for the arguments type. So we do this in various positions. This is actually quite simple. So C types are converted to Haskell using sort of a types table, which maps C type specifiers like int, long, enum something, or a type def thing to Haskell type. This is stored in the context, like I've shown, like the context I was talking about before. Now, interestingly, we also need this table to parse the C declarations, because C grammar is context sensitive. You cannot parse C without knowing what types you have in scope. So this is also needed to parse C declarations correctly. So if you have type def int bool, to parse code using it, you need to know that the type def exists, which is a known inconvenience of parsing C. So the lexer needs to know what types you have, which is a bit strange. Compound C types are just converted using hard-coded rules. So if you have a pointer, it's going to be converted to a Haskell C pointer. We have these types defined already in the Haskell-based library, so we just use that. Pointer and arrays are pointers. Function pointers become function pointers. So this is what it actually looks like. I also have a slide with a very small data type. So this is that type specifiers are just this small definition. You have void, short, long, int, and then struct something, enum something, or type name something. And this is the part which you need for lexing, for parsing C types. And they're generated by type defs, basically. So when you do type def int bool, you're going to have type name bool. And then you have a map from these things to Haskell types. And Haskell types are represented using the template Haskell library, which already includes a view to Haskell types. For C types, we have our own library. We basically, it's bigger than this because this is just type specifiers, but then you have compound types and C declarations, which is actually like the annoying part. Finally, so we have converted the snippet to a function. We have converted the types of this function to Haskell, and so we are able to add an FFI binding to this function that we have just generated. We need to use this function now and apply it to the right arguments, basically. This is the third step. So for default anti-quoters, so if you have $XX, it's just very trivial. You just convert the type, and you expect X to be of the right type. So you just apply it to the function. For more complicated types like the vectors or bystrings or functions, the anti-quoter handles this business. And basically, when you define a new anti-quoter, you need to provide a function that is able to marshal this data. And the way this looks, if we go back to print vector info, and it's kind of C function representation, when we invoke inline C, X, Y, Z, we're going to, the anti-quoter is going to provide us with these backlen and backpointer functions. So backlen takes a vector and then a continuation that uses the length of the vector. Backpointer takes a vector and then again a continuation with the pointer of the vector. And then finally we can apply them to, maybe the other way around, but like we can apply it to the function we generated. So more generally, in the case of these vectors anti-quoters, backlen will roughly provide something that looks like this. Given a vector, I accept a continuation with the length of the vector, and then I run it and return the result. And backpointer does the same, but with the pointer as the argument to the continuation. More generally, if you're anti-quoting something and you want C type B, and the original Haskell type is type A, you want a function of this kind. So it goes from the Haskell type to a continuation that accepts the target C type and then executes it. This sort of continuation passing style is done so we can do resource management with these things. So for example, for function pointers, you need to allocate stuff actually, as you were noticing, that you need to allocate these function pointers, and the anti-quoter can run the continuation, well, allocate it, run the continuation, and free it immediately. So you can do this resource management without leaking stuff, basically. Finally, how do we build these things? Well, the C file, well, we generate for each Haskell file as a corresponding C file, which contains all these functions. And it also contains the includes that we included at the top, for example. And it's placed alongside the Haskell file right now. This is sort of icky. I'm not too happy about how the build system works, but it works very well. And then the C file will have to be compiled and linked along all the other Haskell objects, obviously. If you use Cabal, it so happens that you can just specify the additional C file in the C sources. We got quite lucky here because this is sort of depending on the order in which Cabal compiles things. And it happens to work now, but yeah, I would really like a more flexible build system so that we can specify these relationships and this sort of order of execution of compilation more explicitly. A nice thing is that you can specify the options to the C compiler. You can specify what libraries you have to link with the objects with the same mechanisms that you would if you had proper C files that you had written. You can specify even the C compiler. You can have a great deal of flexibility regarding this, which is what we wanted. We don't want to force on the user a way of compiling the C code. So things I'm not happy about. GHCI doesn't work. These I'm really unhappy about. But it's quite hard to fix. I mean, it is fixable, but like if you're interpreting code that depends on the C code being compiled after you've sort of type checked the code, like it's a pretty unconventional relationship in terms of this pipeline. I would love it to work at some point, but there's no immediate plan. And the other thing is that the build process through Cabal is quite fragile. I would like to, as I said, to have a more explicit way of specifying these dependencies. They can both be fixed, but we need more flexible tooling for sure, at the very least. I also want, I already mentioned this, but this would definitely not be possible without language C inline, which kind of shows that this was possible. And with also Matthew's previous library, which is now called inlineR, from which we took a lot of ideas. And that is all. Thanks for listening.
Whether the generated foreign calls have the safe or unsafe annotation.
Yes. You import, you use a different anti-quoter.
Oh.
You use a different quasi-quoter, sorry.
Okay.
So, by default, so C block, actually, let's go a bit back. Right, so here I'm importing from language C inline. The default is safe calls. There is a .unsafe module that you can use for unsafe calls, so they're faster. There is also a .interruptible module for interruptible calls. I just didn't notice they exist, and somebody told me, you should have this, and he added it, so that was really nice. But yes.
What about C++?
You can compile C++ with this. You specify just a C++ compiler, and you need to link with the C++ standard library. It works, and I have at the back of my mind many ideas how now to not only, well, this is already possible. Objective-C and C++, you can already compile them. You just specify different, well, you can specify with Kabbalah different compiler, but it's enough to just tell it to link with the standard library, and you can change the extension of the files generated. So this is sort of a cheap way to tell GCC or Clang you should compile with C++. Me and Padek actually have plans to actually make the C++ experience pleasant, which requires, no, I mean, this is not C++ fault, to be honest. Like, C++ gets more blame than it needs to in many circumstances. This is just a case, I think, where, for example, we would like to have polymorphism in templates to reflect into polymorphism in Haskell. That would be great, right? This is the main hard difficulty, really. We have some ideas on how to do this by generating code sort of more dynamically, but yeah, we haven't got around to it. We also don't have an immediate need for it, but it will be very nice to have, for sure. This could be handled once you have this support. It's very modular, and so you can just add an anti-quoter to do that. For example, you could already implement an anti-quoter to turn a Haskell string into a char pointer. You can have, like you have back lang and met pointer, you could have string lang and string pointer. I think once we get to the point where the basic interaction is working, in the sense that we understand some basic abstractions that are present in C++, I think we have a solid base where we can expand on it. But we haven't got it. I would love to do it. When I have some time, it'd be very nice to do.
So I didn't quite pick up from the talk. You described how this sort of builds on the work Manuel did with language C inline. And so I was just trying to figure out what are the cases in which I would want to reach for this over that, since they both give very similar things. It seems like one of the differences here is your parser is a lot more lightweight, so it can handle stranger things, maybe? I couldn't quite figure out.
Right. So I think we can divide the differences within sort of fundamental difference and like technicalities, which I have figured out, and Manuel didn't, simply because didn't get around to it yet. So like the second part is sort of less important because I'm sure you could fix it easily. For example, he builds a table of C symbols that needs to be populated at runtime. So you need to initialize, for each module, you need to call a function to actually being able to work with the inline C snippets. This is very inconvenient, but it's possible to avoid this by using a newly added feature of template Haskell that just adds a top-level declaration while you're splicing Haskell expressions. This is a small technicality. Then the differences come down to ergonomics, like in the sense that, like, apart from writing functions writing C functions out of a file, how you actually use the library is just completely different. So the way you specify the target types, the way you anti-quote things, and the way you can add anti-quoters, the way you specify the return type of the whole of the C code. The interface is just completely different. So the similarity is that they both write functions to a C file, and then you can automatically invoke it. But it's, well, I mean, I wanted to do certain things very easily, and I think he wanted to do other things very easily. Like, for example, Objective-C was a big target for him, and we just wanted an interface that worked nicely for us. He also hadn't, this is also a small thing, but he hadn't figured out a nice story for Cabal, for building with Cabal nicely. But again, this is a small technicality. Yeah, I mean, to be honest, I haven't had much contact with him regarding this. Maybe he's very happy with inline C, and maybe he, like, I don't know what he thinks of the differences either. We just, basically, we needed to get this done, and so we just did it. But, yeah.
Okay, so I think we should continue the discussion over lunch, and yeah, we'll have lunch outside now, and the next talk will start at 1:30. Thank you again.